Okay. I am going to pass the sign-in sheet around, and I haven't done this in a while. Well, I missed it on the 17th, then we took the test on the 19th, and then today's the 24th. So if you could, please sign in for the 3 dates that I don't have you for, 17, 19, 24. So today and the previous 2 days. I'm just going to take your word for it. If you were here, you were here. You know what I'm saying? Okay. 3.1, we were supposed to take the test and then start 3.1. I decided to let you go. And that's okay, we'll make up ground. We'll be all right. Okay, so 3.1 is titled Quadratic Functions. And I should probably say that Chapter 3, we should talk about what this is. Chapter 3 is called Polynomial and Rational Functions. Polynomial and rational functions. 3.1 is called quadratic functions. I might have to go get better markers here in a minute. These are all dead. So it's kind of weird because this chapter starts off, it says, hey, we're going to study these things called polynomial functions and then rational functions. And then in 3.1 they talk about quadratic functions. Well, why didn't they mention that up here, right? Well, it turns out that a quadratic function is a type of polynomial function. So we'll get to that later when we get to like 3.4. But for now, don't worry that this is called something other than those two. So I said that there were 6 functions we were going to study in this class, right? Lines, quadratic functions, polynomials, rational functions, exponential functions, logarithmic functions. And that we have to be able to graph all of those by hand without a calculator. And that's like 90% of what this class is about, 80%, all right? So we should all know how to graph a line by now, right? If I give you something like y equals mx plus b, right? Everyone should be able to graph that. Find the y-intercept, use your slope, you're in business, right? So now we study in depth this other type of function called a quadratic function. So let's first look at what a quadratic function looks like when you write it down algebraically. Quadratic function has this form. ax squared plus bx plus c. All quadratic functions can be written that way. Here, the a, the b, and the c are numbers. And I have one more condition. The a here cannot be 0. Why can't the a be 0? What if a was 0? That wouldn't be here, would it? And then what you would have is bx plus c. And bx plus c would almost look like mx plus b. It would almost look like a number in front of x plus a number by itself, wouldn't it? And then that would be a line. So it would not be a quadratic function. So to be quadratic, all we have to have are numbers in front, a number other than 0 in front of x squared, a number, and it can be any number, in front of x, and then a number by itself. If it looks like that, it is a quadratic function. So let me give you some specific examples. That's the general form. So an example, you tell me if this is quadratic or not. It's quadratic? Yes? What's A? B? C? 4. So 3, negative 7, 4. Got it? Would this be a quadratic function? It actually is, because you could look at this as being negative 4x squared. Now, I think if you're saying no because there's not an x in there, right? Well, technically there is. It's just a 0x. and we don't really write it. So is there a number other than 0 in front of x squared? Okay, is there a number in front of x? Yes, but what is it? 0. And then is there a number by itself? Yes, negative 12. So A here is negative 4, B is 0, and C is negative 12. Got it? So that is also a quadratic function. How about this? How about that quadratic? Do you have a number other than 0 in front of x squared? Yes? Do you have a number in front of x? Okay. Do you have a number by itself? Yes. 0, right? There's a 0 out there. Now we don't write it, but it's there, right? So we do have an A. A here is 5. We do have a B, it's 15, and we do have a C, which is 0. So that is all quadratic, also quadratic. One more. That quadratic function? Yes. What's A? Negative 1/3. What's B? 0. What's C? 0, because there's nothing there, right? Okay. So the only condition we have is that we, at the minimum, we have to have an x squared term. Then we could have an x or we could not, or we could have just a number or not, right? Now we studied this. Remember our base functions, the toolbox functions? We said we knew what that looked like, right? Looked like this, like U, like a parabola, right? So we already know what that looks like. And we actually know what happens if we add a number out here, right? We know what happens if we add a number in there with the x, and if we put a negative and how it flips it, moves things around. So I want you to look at this function here. All right? That was just to get you thinking about what we've done before. If I said to take this and I said to graph that, you should be able to graph that. Do a quick little sketch. You would take the parabola, right? You would move it right 1. Then you would, this would do it would make it like more narrow, okay? It would compress it down like this. And then the whole thing would what? Go down 8, right? That's what we did last time. We did a quick sketch, but it had to look like this, right? Let me show you what happens. You know, I said the form of a quadratic was this, wasn't it? So that's what all quadratics must look like. So this does not look like that, does it? So let me turn that into that so you can see how you can convert this one into this one. And it's not that bad. The first thing we have to do is algebraically figure out what x plus 1 squared is. So I'm going to do that as like scratch work on the side here. What's x? Did I say plus 1? X minus 1 squared. What is that? That means that, right? So you have to FOIL or expand. You get x squared minus 2x plus 1. That's what would happen if you put all that together. So imagine that that's now this piece right here. Then this would turn into 2 in front of all that minus 8 still, right? Now distribute the 2 through the parentheses. Are there any questions on what I did there? Distribute the 2 through the parentheses. And you get 2x squared minus 4x plus 2 minus 8. We're almost there. Combine like terms, so I can do 2 minus 8 and get negative 6. And I'll just write this up here. So this would become f of x is equal to 2x squared minus 4x minus 6. And let me, yeah, let's do that. So does that look like the standard, the general form of a quadratic now? Yes? So if I take this away, what I want you to see, okay, the only thing I'm trying to get you to see is that this is a quadratic function, right? It is. To make it look like ax squared plus bx plus c, we have to actually multiply everything out and then collect like terms, and then it looks like what we had before. So a here is 2, right? B is -4, and C is -6. Yes? You can't see that from here, right? You can't, well, the A, this is always true. This will always be your A. But you can't see the -4 in here easily. And you can't see the -6 here easily. You have to actually multiply it out to be able to recover those numbers. Okay? Questions? Now, because of that, because what we've studied before can be converted into this, we actually like to look at quadratics as having 2 different forms. All right, this is the first one, the one I introduced to begin today's class. That's our first form. The other form that we can have would look like this. Okay? These are the 2 forms that we will work with in this class with quadratic functions. You're either going to have it all multiplied out already and have a number in front of x squared, a number in front of x, and a number by itself. Or you're going to have this thing, which was where we shifted around and moved things and flipped, right? One of those 2 forms is what we're going to work with. You follow me? Notice that there are some things that are the same, right? Whatever this number is, will always be this number. So remember I said that 2 looked like it was the same? Well, same thing here. Whatever the number out here is, will be your A. But notice there's no B or no C in here. I call them H and K instead, so that we don't confuse them with those 2. All right. All quadratic functions can look like one of these 2 things. So now let's actually talk about a little bit more in depth about that parabola. Right? We said that these things look like these U's that opened up and down. Let's talk a little bit more about some of the details of a parabola. We have some special points on a parabola and special names for them. So we're going to look at parabolas. Now we said that if you have a parabola or a quadratic function, it has to look like this U. If I come in here and I draw a U, we draw it like this. Everyone agree that there's some quadratic function out there that would draw that for us, right? I don't know what it is, but something out there will draw that. Now there's an important point down here on the very bottom of this parabola, right there. And that would actually be like the lowest point of the parabola, wouldn't it? The lowest point. And it's also looks like it's the point that kind of cuts the parabola in half. Like if you were to look right down the middle and draw a dotted line, although this is not part of the graph, the parabola is kind of like a mirror image of itself over that line, right? If I reflect this over, I would get this side. So that point's very important. This point has a name. It's called the vertex. The vertex of the parabola. And it just so happens that the vertex, since it's a point, it has some x and y coordinate, doesn't it? Like if I want to get to that point, I have to go out a certain distance and then down a certain distance. It will always be hk. Remember I said there was 2 ways you could write a parabola? In one of them, it was ax squared plus bx plus c. The other one was a, then a parentheses, inside was x minus h squared, then plus k. That h and that k actually tell you exactly where that point is. We'll look at examples so you can see how this is going to work out. But now let's talk about some other points. And I'll remind you of these points with this. Remember when we were studying lines? When we first started looking at lines? I said there were really 2 ways to graph a line. One, the first way we learned was to use this method called the intercept method. Do you remember that? Where you tried to find those 2 points where your line hit the x and y axis. We called those the intercepts. And we said that normally, like a line should have an x and a y intercept. Sometimes it doesn't, right? If it's vertical, it only has a what? An x-intercept. If it's horizontal, it only has y-intercept, right? So it's possible for a line to not have one of those. But look at the parabola. How many x-intercepts do I have over here? I have 2, right? I have an x-intercept here. I'm just going to put next to it x-int. And then over here, I have an x-intercept here, x-int. All right? So I have 2 x-intercepts. Do I have a y-intercept? Yes. I have one right here. This dotted line down the center, we call it the axis of symmetry. But I'm not going to ask you for the axis of symmetry in the test, because the vertex is enough information for you to know where this dashed line goes. But just know, later on you might be in a class and for some reason they talk about axis of symmetry. That's this, okay? So those are the main characteristics of parabolas. Every parabola should have a vertex, shouldn't it? Yes? And then you may have x-intercepts and you might have y-intercepts. And I want to talk about that a little more. Is it possible to draw a parabola that does not have x-intercepts? Yes. Sure. So let me give you an example. Or maybe you can help me. How can I draw a parabola that wouldn't have x-intercepts? Okay, if we turn it, are you saying turn it? Well, then it won't be a parabola in the form that we're looking, because if I turn it sideways, it won't be a function. Remember the vertical line test? Right? That would fail the vertical line test. So I'm talking about functions that are parabolas. How can I draw it where it won't? Move what above the x-axis? The vertex. Put the vertex above it, right? If I draw a vertex here, right? And then I draw this parabola so that it goes up like a U, then it will not hit the x-axis, will it? Now, do I have a vertex? Yes. Do I have a y-intercept? Yes. Yes, I do have a y-intercept, but I do not have any x-intercepts. So it is possible to have a quadratic function that does not have x-intercepts. It's also possible to have one that has 2. Is it possible to have 3? If it's a U, keeps going up forever, it's not going to be possible to ever cross the x-axis more than twice, right? Can you have just one? Can you have a parabola with just one x-intercept? So I'm going to put here no x-intercepts here, just so you know, right? How can I draw it? Can I get one with just one? How? Put the vertex on the x-axis. So if I put a vertex, I'll do it in blue so it's a different parabola. If that vertex is the only point that hits the x-axis, then that is one x-intercept, right? Just one. So with all parabolas, you have 3 possibilities in terms of x-intercepts. You can have none, you can have 1, or you can have 2. And that's it. It's not possible to have 3 or 4 or 5. Now, I said we're going to study polynomials, right? What does poly mean? Many. Okay, it turns out polynomials are going to they're going to look like roller coasters. It's going to be things like this. Function that looks like that. Now, how many x-intercepts does that have? 4. 1, 2, 3, 4. So when we study polynomials, we'll start to look at, okay, we're going to have things that may cross the x-axis more than once or twice or 3 times, maybe 10 times. And we'll have to graph these by hand. Okay. Now, let's talk a little bit more about parabolas. What they look like. Yes?
There was 3 ways to have it, right?
Okay, when it comes to x-intercepts, for parabolas, you can only have one of 3 things. You can have no x-intercepts, 1 x-intercept, or 2. 0, 1, or 2. Now, how we're going to determine that, you just have to hang tight. We will actually look at, how we determine if it does or doesn't have those. So I want to look at two different types of parabolas. If a is a positive number, and if a is a negative number. Now, what's a? Does everyone understand that when I say a is greater than 0, I mean a is a positive number? Like 2 or 10 or 3/4 even, right? Fraction, a decimal. As long as it's a positive number, that's what that means. And then this means a is less than 0, so a is a negative number. Now, a in the formulas, the two formulas I gave you, right? I'm writing these very quickly because you already have them. The other one was a x minus 8 squared plus k, right? Those were the two forms. The a was just the number in here in front of x squared, right? If it looked like this form, it's always the number in front of x squared. Or in this form, it's always the number out in front of that parentheses. If the number out in front of x squared or out in front of the parentheses is a positive number, you can guarantee me that the parabola is going to look like this. It's going to open what we call up. Okay? Another kind of cheesy way to look at it is, I said a is positive, right? What do positive people do when you see them walk down? They smile, right? So this is a big smiley face, right? That's real cheesy, but you know, that's the way it is. Okay? Now, if the a is a negative number, then the parabola is going to open down. And that comes from what fact? Remember what happened? What did we do when we had a negative out in front of this? We reflected it over the x-axis, right? So I took that and it made it go down. So that makes sense that it would open down. I hope it makes sense. Now, one thing I will point out here. The A only tells you up and down, okay? The A does not tell you how many x-intercepts you have. Because I can move this whole thing up and I wouldn't have any x-intercepts, right? Or I can move this whole thing down, it wouldn't have any x-intercepts. So A only helps you get up and down. That's it. Questions? So here's what I'm going to do. The way we're going to take the rest of this class, or this section for the rest of this class, is we're going to try and come up with a systematic approach, a set of steps on how to graph a quadratic function by hand. All right? How to do it. Set of steps. These are steps that you would write down on a cheat sheet, so when you came into the test, you would do this, 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 this. All right? So let's talk about graphing. Graphing quadratic functions. And before I do this, let me talk a little bit, because sometimes it's useful for us to actually know what the hell, like why we would study something, right? When we were studying lines, I gave you the first problem on the test was about someone selling cars, right? Lines are really good at describing things that happen in the real world that change linearly. Like when you clock in at work, you get paid so much per hour, then how much you make looks like a line, doesn't it? So lines are perfect at modeling things that behave that way, but not everything in the real world is linear. So I'll give you an example of something that's not linear. Let's say, and I'll do it this way so I don't hurt anyone over here. These are my good markers. I don't want to throw those away. Okay, let's say I take this marker and I throw it across the room. I want you to watch, you know, the path of the marker through across the whiteboard here. Right? All three of those had different paths, right? But they all looked like what? They look kind of like curves like that, but if I throw it a little slower, you might see it there. Right? That path is actually a parabola. Okay, it's parabolic. Everything on Earth or I should say anything, any object on any planet with a gravitational force should travel, if you throw it through the air, should travel in a parabolic path. Should be parabolic. So let's say that I throw a ball, or some baseball guy, right, or girl, whoever, hits a ball, and that ball goes up and then hits the stands, right? And some drunk guy grabs it and is all happy, right? Well, then later on, they say how far that ball would have gone, right? I'm not a big baseball fan, but I know enough to know that even though it stopped here, they can tell you how far it would have gone. And the reason they can is because they know that it's a parabola. And so all they really have to do is find this point. What's that point on the parabola? Look at this parabola. If I draw this and I say, okay, where he started, this is my x-axis and this is my y-axis, then that point represents a what? The x-intercept, right? So if you can find the x-intercept of this parabola, then you know exactly how far you are away from the guy, don't you? The question would be, how do they come up with the function? How do they come up with the parabola? And there's ways to do it. It's pretty easy. All you need is something to measure 3 points on the parabola and you're done. So it's called regression analysis, and we don't do it in here, unfortunately. We never study how the functions come about. We just study the functions themselves. Another example of parabolas. Anybody here ever use a cell phone? Or let's just say anytime you watch TV, or you watch anyone watching World Cup or anything like that. Okay, if I'm trying to communicate, I'm on this side of the world, right? And I'm trying to communicate with somebody on this side of the world, right? There's no straight line path to them. So how do we communicate with them? We send a signal, electronic signal, up to a satellite. That satellite is up here in space. It sends that over to another satellite, and then that beams that back down to that person, right? So we go up and around the Earth. Well, the thing that catches the signal is a dish, right? A dish sitting up there. And people have them on their apartments, right? Anyone has dish TV or whatever. Got these little dishes on their roof of their house or on their balcony of their apartment, right? And that dish looks something like this, right? And it's got this little thing in the middle. I don't know, something like that, right? If you take that dish and you cut it in half and look at it from the side, and you have that little thing coming out like this, this shape of this is not just some random shape that they were like, okay, yeah, we'll manufacture these and we'll just bend it and just whatever. It has to be a parabola. It has to be a perfect parabola in order for this to work. Because what happens is the signal that's being sent out, right? When you send a signal out, it doesn't go in one direction, it goes in every direction. So you send the signal out, and then that satellite has to catch it. And so what happens is the signal comes into this, and what happens when it hits there? It bounces, right? And it bounces and actually goes right to this little receiver. And then if you come in and you hit it like this, it'll bounce in the perfect angle with the parabola. It will bounce exactly to that receiver. And anything that comes in will bounce exactly to that receiver. So what happens is this very, very weak signal becomes amplified, becomes focused onto one point, and it becomes a strong signal. And so you're able to communicate, right? But you have to have a parabola to do that. Anybody have one of those flashlights where you take it and you turn it and the beam of light gets wider or gets more narrow? Y'all ever seen that?
Yes.
Yes? You know what I'm talking about? Okay. Same principle. You have a flashlight, you have a light bulb, okay, that's emitting light in every direction. Here's your flashlight, okay? Right. And what you do is you turn this thing and it changes the beam. Well, what's happening is there is a parabola in there and it's a mirror, a reflective mirror. And when you turn that, what happens is it moves the parabola back and forth. And what it does is the light comes out, and if you have it turned just perfectly, it'll bounce those light beams straight out. So you get this very focused beam. But if you turn it and you pull that parabola back, things don't come out normal. they come out at an angle instead, and they come off, instead of coming straight out, they come out at angles, and it spreads the beam out. But again, it's all parabolas that are required to do that. So that's just some examples of real-life parabolas uses and why it's useful to study them. Any military people here? You don't have to admit it, but I mean, what's one of the main things that has driven the evolution of technology in the world? What's driven it? I mean, like, what is really, when you look at like scientific progress, what usually always drives it? War, right? The need to kill people, right? Efficiently, quickly, right? War. Think about all the, World War II, all the technology that was developed, right? If you're just, back in the day, if you're just trying to conquer a castle, okay, right? You got a castle sitting out there, and you want to launch, some artillery out of some, artillery piece out here, and you want to launch this thing out there, you can just start lobbing just things at it and hope to hit it. But if you've studied the quadratic function, then you no longer have to guess. All you have to do is adjust everything properly, and you know where it's going to land, and there's no question. So anyone in modern day military that's been in artillery, it's all just tables, and it's all just, you just dial it in, and it goes where you want to go, where you want it to go. Because that's all been figured out already. Okay, you ready to graph these? Sorry, I kind of went off there a little bit. All right, so here's the first thing that we're going to do. First step always, identify the form. All right, we want to identify the form. Now, I said there were two forms, right? We could have form, we'll call it form A, which would be f of x is ax squared plus bx plus c. And then the other form, it could possibly be, is this one. We've got to know what we're looking at before we start trying to graph it. After we've identified the form, the next thing we're going to do is determine if it opens up or down. Does it open up or down? Now, how can you determine that? Just by looking at A, right? So I'll just remind you here, A greater than 0 means up, A less than 0 means down. Do you think that that would be pretty easy to do? Just right off the bat? I mean, someone gives you a quadratic function, you can determine if it's up or down? What other things are we going to need? Well, how about the vertex? Every parabola has a vertex, doesn't it? Yes? So let's let that be our next step, trying to find the vertex. So step 3, find the vertex. Now this couldn't be easy or it can be a challenge. All right? It depends on the function, the way it was given to you. All right? So we have two cases, right? We have two scenarios, depending on the type of function that we were looking at. If it's the type f of x equals ax squared plus bx plus c, if we're given that form, the only way to get the vertex is with a formula that I'm about to give you. It's called the vertex formula. And here's what it says. Remember the vertex was the point HK, right? The vertex is the point HK in our picture. So the formula says that if you're given this type right here, h will always be negative b over 2 times a. That means you'll have to take whatever number's out here, switch its sign, and divide by 2 times whatever number's in front of the x squared. That will guaranteed always be h. We're going to work through an example, don't worry. All right, we're just trying to get it all laid out first. And then to get k, what we do is we compute this. Now what the hell does that mean? We substitute what we just got, right? Whatever this is, we plug that into the function. Whatever we get out is our k. And that will give us our vertex. Okay, so that's what we do if it's that first type. You all right? Okay, go do some jumping jacks or something. A power nap or what? Okay, what if we're given the other type? Anybody see what happens if we're given the other type? We actually know what h and k are, don't we? And that's the best case, because that's the easy case, all right? The easiest thing is when it's given to us like this, because we can actually identify what h and k are just by looking at the function. Kind of like the same way we knew what a was, just by looking, we'll be able to know what h and k are. Okay, so we have a way of determining if it went up and down, right? We have a way of determining where that vertex is. What do you think we should go for next? The intercepts, right? But, hold on. I do something a little bit different here. And you'll see why. We're going to do, our fourth step for us is to do a quick sketch. We're going to do a very quick sketch of what we have at this point. Now think through why I want to do this, okay? What if right now, don't write this down, okay? What if right now I know that my vertex is here and I open up? What can you tell me? I don't have any x-intercepts. So why should I go waste my time trying to find them? Understand? Okay, what if I get something like this? And it opens down. I do have an x-intercept, so I'm going to need to go find it, right? Or if I have something like this, and it opens down, what can I say? I'm going to have 2 x-intercepts. So I need to go find them, right? So this step right here is just to avoid us doing unnecessary work if we don't have to. Like right here. We wouldn't want to go and try and find x-intercepts. So we do our quick sketch. And then step 5, we say, how many x-intercepts? How many do we have? So that'll depend, right, on the problem? So if we have none, what? Skip, right? If none, skip this step, right? Skip this step. What if we have 1 or 2? How do we find x-intercepts? Do you remember how we found x-intercepts when we were doing lines? You set y to 0, didn't you? You set y to 0. Now, with our functions, we don't have y, do we? But what did we replace the y with when we came up with this function notation? I mean, that f of x didn't that used to be the y and we just called the y f of x instead? So like this used to be the y, didn't it? So instead of saying we're going to set y to 0, we're actually going to say set the entire function to 0. So if we have 1 or 2 x-intercepts, we will set the function equal to 0 and solve for x. that step is going to be a little bit difficult sometimes. Do I remember when in the beginning of this class I was talking about why do we have to take this class and what's the purpose? And I came up and I said, look, to me it's about procedures. It's about can you follow steps? If someone gives you these things to do, can you go carry them out? This is our first example of where I give you a set of steps, and now it's all about can you carry them out. All right. So we will either not have any x-intercepts and we will move on, or we will have one or two and we will have to actually solve an equation, won't we? And then we will have them. And then what should we go find? So we have vertex, we have x-intercepts, y-intercept, right? So what about the y-intercept? Find y-intercepts. Now, will you have y-intercepts? Think about that for a second. If I tell you to draw a parabola, any way you want, is it possible to draw it and it not have a y-intercept? It's impossible. Doesn't matter. I mean, now, if of course we turn it sideways, but then it's not a function. So no matter how I draw a parabola, right? Doesn't matter how I do it. I'm going to have to cross through the y-axis at some point in time. So I have to have a y-intercept. And how do we find y-intercepts? How do we find a y-intercept with a line? We set x to 0, didn't we? Well, for us, setting x to 0 means plugging 0 in for x, right? Isn't that the same as doing this? Find f of 0. Doesn't f of 0 mean plug 0 in for x into the function? So that's what I'm doing. And now your final step is to do a final picture. Put it all together, draw it. Final sketch. All right, we ready? Those are the steps. Now it's actually time to carry out some examples. All right, here's our first example. Sketch f of x equals -2 times x plus 4 squared plus 8. Now, what I do want you to understand right now is that I could have given you that on the last test, couldn't I? Right? I could have, and you would have done that pretty quickly. You would have been like, oh, I'm going to move it to the left 4, right? And then you would say, I'm going to flip it and do some shrink or whatever on it and then move it up 8, right? That's no longer what I mean by sketch. Now what I mean by sketch is go through the 7-step process. That quick little sketch of moving things around is no longer good enough. All right, first step. What's the form that we have? It's that one, isn't it? It's that one. As soon as you know the form, you can continue on. What's the second step? Does it open up or down? In this case, what? It opens down. Why? Because A is what? -2, right? That's a negative number, it's less than 0. So I know it opens down. All right, moving right along. Third step is to find the vertex. The vertex is the point HK. Here's the one tricky part to this. Be very careful with this, because if you mess this up on the test, it's going to throw everything off, right? Notice in the formula, it says x minus h, doesn't it? And up here it says we have plus 4. your h value will always be opposite of what you see. So if you see a positive 4, your h is going to be negative 4. It's always that way for h, opposite of what you see. And that has something to do with the whole thing of how we moved it opposite of what we thought, left and right. Same sort of logic there. So what's h for us here? Negative 4. Now k is exactly what you see out here by itself, which for us is just 8. So I have my vertex. Didn't have to do a whole lot of work for that, right? Just had to be careful on the sign. Careful, all right? Opposite of what you see. So what if this had said x minus 4? It would have been positive 4. All right, have we finished up step 3? Right? Step 3 said if we had this form, which we did, then we would just figure out what h and k are and be done. Fourth step is a what? A quick sketch. So when we say quick sketch, I mean quick sketch. It doesn't have to be fancy. And the only thing I'm going to put on this is the only real piece of information I have, which is I have a vertex, right? Negative 4, 8. That means I move to the left 4, up 8. And I have a vertex there. And which way does my parabola open? Down. What does that tell me? I have 2 of them, right? I have 2 x-intercepts. So step 4 is this quick sketch. Questions? Step 5? How many x-intercepts do you have? 2 x-intercepts. How do you find the x-intercepts? You set the entire function, right, equal to 0. This is going to be the hardest part of the entire problem, right? This part right here. So I need to take my function and set it equal to 0. So here's what it's going to look like. My function was negative 2 x plus 4 squared plus 8, right? That was the actual function. And I want to know when that's equal to 0. Now here's where we have to start drawing on some knowledge that we should have prior to coming into this class, which is solving quadratic equations. This is a quadratic equation, right? You have an x in here, it's squared, you have an equation. So anytime we have this form, right? A x minus 8 squared plus k, anytime we have it, the way we solve it is always going to be the same. Here's how we do it. We are going to get this whole thing right here by itself on one side of the equation. So how could I get that by itself? What would the first thing I need to do be? I could subtract 8 on both sides. Is that fair? Subtract 8, subtract 8. All right. If I do that, I'm left with the negative 2 sitting in front of x plus 4 squared. Now I have on the other side negative 8. Now remember, I'm trying to get this by itself. I need to get rid of the negative 2 out front. So what do I do to get rid of the negative 2? Divide by negative 2. Right? Not add 2. This is multiplication. I need to undo multiplication. So I divide both sides by negative 2. And when I do that, I get what? The x plus 4 squared over here equals 4. Now, do I have that thing by itself now? Yes? So now, I'm going to come in and kill off the squared. The only way I can kill off a squared is to come in with the square root on both sides. Right? That's what I'm going to do. So on the next step, and I'll rewrite the whole thing, I'm going to take the square root of the left side, and whatever I do on the left, I do on the right. There's one more thing, though. I told you when we were doing domains that when you come in and you take square root on both sides, what do you always have to do? Plus or minus. So I have to put a plus or minus on this over here. What is the square root of all that stuff squared? What's going to happen on the left? This cancels this out, right? And you're just left with x plus 4. On the right side, what is the square root of 4? 2, but then I have plus or minus, so I have plus or minus 2. We are almost done. I almost have x by itself. All I need to do now is what? Subtract 4, right? Subtract 4. Now be careful with this step. When you subtract 4 here and subtract 4 here, here's the way you should write this. On the left side, the 4's cancel, right? On the right side, this represents two different numbers, right? It's positive 2 and negative 2. So the way I'm going to write this is as follows. Plus or minus 2, and then I'm going to subtract 4, right? Now what I'd like to do is I'd like for everyone to realize that this generates two different answers. I get one answer if I use the plus, right? And I get another answer if I use the minus. What if it's plus 2? What's plus 2 take away 4? Negative 2. And then what's negative 2? So I'm treating the 2 as a negative now. Negative 2 minus 4 is going to give us what? Negative 6. These are the two places that we hit our x-axis, at negative 2 and negative 6. So we could actually look at these as points, negative 2, 0, and negative 6, 0. Understand? Those are x-intercepts. So that was a little bit of work to get those x-intercepts, right? What's the next step after x-intercepts? Y-intercept, so that's step 6, right? To find the y-intercept, what we do is we plug 0 into the function, right? Into our function. So that means we take our function, which was negative 2, and then it was x plus 4, right? So I'm going to, instead of saying x plus 4, I'm going to say 0 plus 4, and then squared, and then, was it plus 8? Do you see that that's the original function with 0 plugged in? Which is something that you had to do on your last test, right? I give you a function, I tell you to plug in a number. That's all we're doing is plugging in 0. All right, let's be careful with order of operations here. We do what's in parentheses first. 0 plus 4 is what? 4. 4 squared comes before the negative 2, right? 4 squared is 16. So we have negative 2 times 16 plus 8. That's negative 32 plus 8. So we do that multiplication before we do that addition. And what is that? Negative 24. And that is my y-intercept, isn't it? It's my y-intercept. So as a point, it would look like this. 0, negative 24. Right? We plugged in 0 for x. The function spit out negative 24. That's all the information I need, right? Now I should be able to draw a pretty accurate graph of this quadratic function. So that's part 7, is the graph. Can I erase this? Anyone need that still? All right. So when I go to graph this, I need to think before I graph it, all right? I had my vertex, I'm going to call it V, it was negative 4, 8, right? I had x-intercepts, they were, what was it, negative 6, 0, is that right? And then negative 2, 0. Then I had a y-intercept that was 0, negative 24. Let's take a look at our x values. What's the largest x value I need? Like, look, I have 0, right? X is 0. And then I have, what, a negative 2 that's here, negative 6 is over here, negative 4 is over here, right? So I'm mostly going to be working on that side of the graph. And then y values, what's the biggest y value I have? 8, and then the smallest would be negative 24, right? So I need to make sure my graph goes all the way down to negative 24 to cover everything. Yes? So when I go to do my graph, maybe I should have done this. You see how that would be a better fit for what I have? On the x-axis, I just need to have something at 0 Let me count to -6. So -1, -2, -3, -4, -5, -6. Part of what I'll be counting off for on the test is how, if your graph is like labeled appropriately, everything's drawn correctly. So you want to make sure you take the time to kind of think this out before you just throw something out there. What about my y's? Do you want to count by ones? I need to go up to 8 and down to -24, right? I could count by 2s, I could count by 4s, I could actually count by 8s, couldn't I? I just got kind of lucky, 8 and 24 are multiples. So let me count by 2s. 2, 4, 6, 8. That's 8, right? And then down, I have to keep that same scale. So 2, 4, 6, 8, 10. I'll put -10 there. 12, 14, 16, 18, 20. There's -20. 2, 24. There's -24. Remember what I said before when we were doing lines. Your scales can be different in the y and the x direction, right? How much this measures in the x direction does not have to be the same as how much it measures in the y. All right, let's plot our points. Let's start with the vertex. -4, 8 was to the left 4 and up 8. X-intercept was at -6, 0. That's here. Another x-intercept was at -2, 0. And a y-intercept at 0, -24, which is down here. And your vertex is the highest point, right? It's the highest point. And this thing needs to look like a U, right? Not like a V, like a U. So the way that I like to do this is I kind of force it to be a U up here first. Like, I kind of force the action that first. So I know it's going to be a U. And then what I do is I work on the side of the parabola that I have more points on. So I have 2 points on the right side, don't I? So I'm just going to kind of eyeball this in like that. Okay. And then I draw the other side, and what might help you draw the other side pretty accurately is to imagine that thing that we call the axis of symmetry going down the middle. If you draw the axis of symmetry, it helps you see the mirroring. Like you wouldn't want to draw this, right? That doesn't look very symmetric, right? So you go for something more like this. Does that look better? It doesn't have to be perfect, okay? But the things I need to see are where these points are. Those have to be accurate. And it needs to be a U-shaped. And it obviously opens down, doesn't it? That took a little while, didn't it? A process, a set of steps. So how about we take a quick, is it already time for a break? I think it is. We start at 2, right? Yeah. So we'll come back at 3:30, and we'll have to give you an example of the other type, right? And then we're going to move on to the next sections. So take a little break. Okay, so what we're going to do now is we're going to sketch, I put the homework assignment over here. So the book does not, so scratch what's on the schedule. Where's the sign-in sheet, by the way? It's on there. Forget the assignment that's on here for 3.1.
I'm sorry. Can you pass that?
Yeah, okay. So, and just do this. So I want you to sketch that problem and then do these 4 problems, all right? You'll get this. Let's go ahead and send it back. All right, so first step here is to identify what type of quadratic we have. So the type we have here is ax squared plus bx plus c, right? That's the type we have. Does this thing open up or down? Opens up because a is 3 which is greater than 0. So it's a positive number. So this parabola should open up for us. What's our third step? Vertex, right? So our third step. How do we find the vertex if we're given a quadratic function in this form? We don't have HK just sitting there staring at us, right? Right? So we have to use that formula I gave you. The formula said to get HK, H would always be negative B divided by 2 times A, wouldn't it? According to what I said? Now, for us, what is negative B? It's the opposite of B, isn't it? What's B for us? Negative 12. So what's the opposite of negative 12? Positive 12. What happens if you mess that sign up on the test? The whole thing's going to be off, okay? Your vertex is going to be all out of whack. So that sign thing you have to be careful with there. Divided by what? 2 times A, what's A? 3. So 2 times 3 is 6. And so 12 divided by 6 is 2. Notice how that turned out to be a nice number, too? Not every quadratic function will have a nice number for the h. Sometimes this will be a fraction. It'll be a decimal sometimes. I'm going to promise you that on the test, I'll keep the numbers nice, okay? Nice integers. How do we get k? What do your notes say? It's f of h, right? So we plug h, whatever we got, 2, into the function. So do you see that if you don't get 2 correct, then what you plug in is going to be incorrect also. So it's very important you get this number correctly. F of 2 means you go up here and you plug 2 in. So that will be 3 times 2 squared minus 12 times 2 plus 8. Square the 2 first, that's 4. 3 times 4 is 12. So we have 12. And we have 12 times 2 is 24, but we're subtracting it, so minus 24, then plus 8. What does that give you? Negative 4. So what is our vertex? It is the point 2, negative 4. You happy with that? The h is 2, the k is negative 4. Now what is our fourth step? A quick little sketch to see what's going on, right? So here's my quick sketch. My vertex is at 2, negative 4, out to the right 2, down 4. And this thing opens which way? Up. So I'm going to have 2x intercepts. So I know I'm going to need to find them, right? So that's step 4, quick little sketch. Step 5. I have 2x intercepts. So how do we find the x-intercepts for a function? Set it to 0, right? So I need to take the original function, which was 3x squared minus 12x plus 8. I need to set that equal to 0. All right. This was kind of the more challenging part of the previous problem we did also, right? We had to move things around, take square root on both sides. That's what we did when we had it in the other form. But whenever you're in this form, you don't do it that way. You don't try and get anything by itself and take square root. Anyone have any recommendations on how we could solve this? You could try factoring the left side. If that doesn't work, what can we use? What type of equation is this? a quadratic. What do we have to solve any quadratic equation? Quadratic formula? Do I remember hearing that? Remember the quadratic formula? You may not remember it, but maybe at some point in time you were shown a quadratic formula. So let me try factoring first, because factoring is always going to be the quicker, easier way if I'm good at factoring. So do I have a GCF on the left side? No, right? No GCF? All right, so there's 3 terms on the left side. So let me try this. This all ring a bell, what I'm doing here? 3 times, it's AC method, 3 times 8 is 24. And then I have the number negative 12 here. Can you come up with 2 numbers that multiply to be 24 and add up to be negative 12? So what are the factors of 24? There's 1 and 24, there's 2 and 12, there's 3 and 8, there's 4 and 6. That's it, right? Can I get any combination of these to get close to 12? Negative 3, that gives me 11, right? So I can't get it to negative. So this is not going to work. Okay, see that? You can try factoring, it's not going to work. So factoring fails. So I am going to employ the quadratic formula. Now this is its own little note here. I'm going to just remind everyone right now what the quadratic formula is. Quadratic formula says that if you have this, which is a quadratic equation, right? If we have this, which is exactly what we do have, right? Then the answers, x, that make this equation true are negative b plus or minus the square root b squared minus 4ac, the entire thing divided by 2 times a. I don't require you to memorize that, but I sure as heck expect you to have it written down on the, when you're sitting there taking your test, or if you're coming into class or doing your homework, you should just have that readily available. All the formula requires we do is plug in the values of B, A, and C in here, and then grind out the answer, and that's our solution. We'll actually have 2 solutions. Do y'all remember that? Ever seen that before? One time, yeah, a long time ago. So let's use it, because if you've done some work with the quadratic formula in the past, you realize that it is just what we call plug and chug. It is just plugging numbers in and chugging out an answer. But there's a lot of room for error here. There's little things with signs you have to be careful with. So here I go. I'm going to use the quadratic formula on this equation. What is A for me in this problem? What's B? Negative 12. And what's C? Is 8. So my solutions, x, will be equal to, what is negative b? It's the opposite of negative 12, right? So it's going to be positive 12, plus or minus the square root of. Now tell me a little bit about b squared. That's always going to be what? Positive, right? Always, no matter what. I don't care what b is. When I square it, it's going to be positive. So what's negative 12 squared? 144? Okay, then I have minus 4 times A times C. So I'm just going to write down what A is. A is 3. What's C? 8. Put that here. And then the entire thing. And notice my division bar goes all the way across. It's even underneath the 12. And on the bottom I get what? 2 times A, which is 2 times 3. All right, so that's like everything plugged in. And now I need to actually grind an answer out here. So x will be equal to 12 plus or minus the square root of, all right, here's, like I said, there's lots of little room for error in this thing. Here's where most people make the mistake. is putting these three numbers together here. Right? People mess up the sign. Someone will say, oh, that's a positive or that's a negative. In all the years of me teaching this, the thing I think most people remember is that what you can do is you can count how many negatives you have. Okay? I have -4, right? That's one number. That's one negative. And then that's it. So I have one negative number. That means when I put these together, I'm going to wind up subtracting whatever I get. If I have two negative numbers, what do you think will happen? It'll be plus. What if I have all three negatives? It'll be negative. So one negative, it's negative. Two negatives, it's positive. Three negatives, it's negative. So just like if you're multiplying, right? One negative, we give you negative. Two negatives become positive. Three negatives stays negative. So I look at this as being one negative and two positives. So what is 4 times 3? 12. What's 12 times 8? What is it? So it'll be -96. And I have the 144 in front of it, right? All over 6. And the last thing, what's 144 take away 96? What do we get? 48? All over 6. With me? Now at this point, you must break your calculator out. Because, I mean, we have two answers here. We have 12 plus this number divided by 6, and we have 12 minus this number divided by 6. The problem is we don't really have a good idea of what the square root of 48 is. So we are going to get our calculators out and get a decimal approximation of square root of 48. So get your calculator out, or if you only have your phone today, that's fine. Now let's find the square root of 48. And everyone here should be able to do this on their calculator. This is expected. When I do it, square root of 48, my calculator says 6.92, oh no, I said 92, but I wrote 29. 6.92820323. That's what my calculator says. Now, we obviously don't need that many decimals. So the question is, how many do we need? And I'm only going to require that you go one decimal. Okay? So 6.9 is fine here. Right? I will also ask you not to round. Because what if this was like let's say that this next number here was a 7. Then you would round the 9 up, right? And that would round that up to a 7. I don't want that. I just leave it as just whatever the first decimal is, just write that down, 6.9. Okay. Again, I see a lot of people make this mistake right here. It's 12 plus or minus what? 6.9, right? The square root is gone. I'll see people and they'll write the square root again. They'll put 6.9 here. That's incorrect, right? You already took the square root of 48. So the square root vanishes. And now we have over 6. Let me point out another mistake I see. People, before they do the square root of 48, they try and divide 6 into 48. Why can you not do this 6 into 48? Well, because the division bar goes all the way across, okay? Some people will draw it and they'll write their division bar like that, and then they'll say, oh, that's 48 divided by 6. I do that first, then I do square root. No. The division by 6 is the last thing you're going to do. Any questions up to this point? Now, I'm going to look at two answers. One with the plus and one with the minus. I'll circle them this time. So if I do the plus, then I'm trying to do 12 plus 6.9 divided by 6. What's 12 plus 6.9? 18.9. Divide that by 6. So now on your calculator, take 18.9 divided by 6 and tell me what you get. 3.15? And I'll just say 3.1 again. So I'm rounding. It's okay. It's okay to round a little bit here. we were trying to kill a bunch of people behind a wall, we might be a little bit more precise about things, right? We'll just use a bigger bomb, not care. 12 take away 6.9. So now I'm going to do the subtraction, right? I'm treating this like a minus, and then divide by 6. What's that? 12 minus 6.9, 5.1. Divide that by 6, and you get 0.85. So what did it say, 0.8? And I really wouldn't care if you said 0.9 here. I mean, I would look at all this and be like, okay, yes, 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 yes. Okay, they're a little off on that. We're fine. Whew. What do these represent again? What the hell is this? X-intercepts, right? So these were 2 points, 3.10, and the other one is 0.80, right? So that's what we finally got to here. Whew. Yeah. That is step 5. So step 6. Y-intercept, right? Find the y-intercept, which we will always have one. We plug 0 into the function. Do you see how nice it is to plug 0 into this particular function? Go back and look at your function. This is 3 times 0 squared. What was it? Minus 12 times 0. Is it plus 8? Right? Wasn't that it? All you're going to get is the 8. Like everything else is gone except the 8. So this is 0, 8 for your y-intercept. In fact, what could you tell me about this? If someone gives you a quadratic function and it's written in this form, what is that c? It's always your y-intercept, isn't it? Because when you plug 0 in, these will always go away. So this, if you look back at like when we did lines, the b was the y-intercept, that number on the outside. Well, with quadratic functions, in this form, the c is your y-intercept. Without fail, always. Okay. 7th step is to graph it. So let me put down all the points. Let's see, my vertex, boy, that was so long ago. Was it 2, -4? Okay. And then I got those x-intercepts. Those were 3.10, right? And then 0.80, correct? And then my y-intercept I just got was 0.8. And so what about my x's? The biggest x I need is what, 3.1? Right, I'm looking at all my x coordinates. The biggest one I have is 3.1. The smallest I have is 0. So I really just need to be kind of on the right side. And then my y values, the smallest I have is -4 and the biggest I have is 8. So I just need to make sure my graph will fit all of that. With me? So this I'm going to have more y-axis going up than down, so it'll do something like this. Seem right? I'm going to count off 1, 2, 3, 4 like that. And then up and down, I'll count by 2s. 2, 4, 6, 8, 2, 4. So -4 is here. Starting with the vertex, I move to the right 2. I go down 4. So somewhere around there. That's my vertex. So that's the lowest point on my graph, right? Because this thing opens up. My x-intercepts. So watch how I do my x-intercepts. I didn't put 3.1 on here, did I? I know it's just slightly to the right of 3. Right, 3.1 is just slightly to the right. So I'm going to put my dot here. Now, when I'm grading your test and I'm looking at your graph, I will look to see if you're to the right of 3, but my most important thing is this right here, that you have your work that shows how you got your x-intercepts. I see you have 3.1 there. Whether or not you got it perfect on the graph, no big deal. Where is the next intercept? 0.8. So again, this would be halfway, right? 0.5. And then half of that would be 0.75. So maybe a little bit to the right of that. So again, we're not trying to land a man on the moon here, right? We're just trying to draw a freaking picture in a class. So you just can't obviously have your x-intercept over here somewhere. Y-intercept, 0.8. It's here. I'm going to come in here with my axis of symmetry, which comes down the middle. And that point I put down there isn't very good, so I'm going to move it. And then I'm going to draw the side of the parabola that has more information. So I'm going to draw the right side. I'm going to start by making sure this is curvy down here. And I'm going to try and just make this thing go through here. It's pretty steep, isn't it? And then I just try and do the same sort of thing on the other side. I'm done. Got it? Okay, a couple of things to look out for, okay, before we move on, because we do need to move on. A couple of things to be careful with. When you're doing your work, if you come and you have a vertex here, and you have x-intercepts here, a y-intercept here, what would you say to yourself?
What happened?
I'll keep my language nice, but you messed up, right? Something's wrong? Something is wrong. Do not ever get that on a test and then try and draw me some crazy parabola that does this. Okay? Because that obviously cannot be a parabola. The parabola has, you laugh, I laugh too when I see it on the test because I tell people in class, do not do that. That means something's wrong. Most likely, one of two things is wrong here. Either your vertex is off or your x-intercepts are off. Usually the y-intercept most people get. So unfortunately, if you get to that point, you're going to have to go back to the beginning and just kind of look through the math again, make sure everything. But if it does look, you know, this all lined up real nice, didn't it? If you get to the point at the end where everything looks nice and symmetric, then you can feel pretty good about you having the right answer there. Okay. I have to move on, but let me just give you one last example here. I'm going to move extremely fast through this, all right? Mostly because you can go back and watch it on the video. This thing has the form ax squared plus bx plus c, doesn't it? It opens which way? Up. Okay. The vertex. Ooh. Vertex. Vertex, I get h, right, which is negative b over 2a. What's b? I don't have a b, right? There's no b, so it's a 0. So what's 0 over 2 times, what's a for us? A is 1. So what's 0 over 1? It doesn't matter, right? 0? So my h is 0. Okay, what do I get when I plug 0 into this? When I plug 0 into this, I get 1. So my vertex is 0, 1, isn't it? Yeah. That was quick work through that. My fourth step is to find a quick sketch. So 0, 1 is here, isn't it? Which way do I open? Up. What does that mean? No x-intercepts. So step 5, I skip. Right? Step 6 is a y-intercept. What's the y-intercept? We'll plug 0 in, you get 1, right? We already knew that. We had that here, didn't we? So how are you going to draw this if you only really have one point? Y'all see what I'm saying? Like if I go to my 7th step, which is to sketch this, The only information I have is that point, right? That is the vertex, that is the y-intercept. I don't have x-intercepts. Any ideas? Yes, just plug in something for x, anything you want. Anything you want. What would happen if I plug 2 into the function? Or let's go with 1. What would happen if I plug 1 in? What would I get? You get 2, wouldn't you? So that means this point, 1, 2, lives on my graph. So if I go out to the right 1 and go up 2, I have a point there. My axis of symmetry is down the middle, isn't it? So all I'd have to do is, draw my little curve and go through that. Now, if I wanted to get a better picture, I could go for another point. What happens if I plug in 2? 2 squared, 4, so add 1, 5, so you get 5. So that means if I go out 2, I'm up here at 5. And that gives me an even better picture. And when you feel comfortable, which I think at this point I would just draw my little curve. Here's my axis of symmetry. I go like this, and then I just try and do the same thing on the other side, and then I'm done. Now, I am not going to give you something like that on a test because this kind of defeats the whole purpose. I want to be able to see you go through all the steps and have to actually execute finding all this stuff. But if it turns out that you face another problem somewhere else, I don't want you to freak out when you're like, oh, wait a minute, what do I do? I only have 1 point. You just pick a couple of other tests, we call these test points, test them, plug them into the function, get a couple of values, and then you're off to go, off and rolling with it. Okay? Why don't we just do a bunch of test points to begin with? What if I had a parabola that went like this? And I didn't know it looked like that, but I picked a couple of test points and I got this point, and let's say I had one other point here. Then wouldn't this parabola work also? Like if I drew it this way? You see, like you could have the wrong parabola if you only just were picking random points. So the process is what's important. Are you ready to move on? Good. You'll have homework. You go through that. You'll have your practice. Okay? 4 o'clock. Geez, that ate up a lot of time. I'm squeezing 3.2 and 3.3 together because the concepts are very much connected to each other. 3.2, 3.3, we're going to call it synthetic division and factoring. Synthetic division and factoring. Now for most students, not all of you, but for most of you, this is where college algebra begins. Like this is the new stuff. How many of you had graphed parabolas or quadratic functions before? Okay, so most of this has been reviewed. This usually is where we kind of start doing things that you haven't seen. All right? Just want to warn you. All right, where to begin? Let's first establish what a polynomial is. A polynomial, again, is something you have seen. But now when we talk about polynomials, what we're going to be looking at are things like this. 3x cubed minus 4x squared plus x minus 1. That is a polynomial. Poly meaning many. Nomial, remember like binomial, trinomial, right? Have you heard that before? Binomial meant 2 terms. Trinomial meant 3 terms. Polynomial means many terms. So this just means many terms. I have 1 term, 2 terms, 3 terms, 4 terms here, right? And also notice that each of my terms has a variable in it, well, except for the constant. And each of those is raised to an integer power, right? X cubed, x squared, x to the first. Here there's no x. That's a polynomial, okay? Would this be a polynomial? Yes. You have multiple terms. What we have an x to a nice integer, 7, x to the 4th. Does it matter that there's not an x to the 6th? Doesn't matter. Does it matter that there's not an x to the 3rd, x squared? That's okay. Just like before when we were looking at quadratic functions, it's okay if certain ones are missing. We just had to have that one out front, right, the squared one. It's kind of the same thing with polynomials. It's okay if things are missing. Now, with polynomials, we have two special things when we look at them. Actually, three things we need to look at. First of all, we talked about descending order, right? Descending order meant highest power down. So the highest power of x and then down. That's called descending order. So if a polynomial is written in descending order, then that first term on each of these has two special things. First of all, they each have something called the leading coefficient. The leading coefficient is the number that's in front of the x. So what's the leading coefficient in that first one? It's the 3. Okay, it's the number in front, so that's 3. And then it has what's called its degree. The degree of this polynomial is the highest power of x that you see. So what's the highest power of x that we see here in this one? 3, right? So it just turns out that in this problem, the degree and the leading coefficient are the same. How about on the next one? What's the leading coefficient on the second one? I'm going to call it LC from now on, meaning leading coefficient. What is the leading coefficient? 10? Is that what you said? What's the degree? Degree is 7. With the quadratic function, what's the degree of a quadratic function? What we were just looking at a second ago. Those quadratics are degree 2, right? What's the degree of a line? What's the power on x with a line? 1. So polynomials are actually, they describe a lot of things. As long as you've got x's to powers, you have a polynomial. Now if we throw a function in front of it like this, then now we have a polynomial function. And over here, if we throw a function in front like that, then we have a polynomial function. Understand? Okay, so we'll get to the functions in a second. We're not ready for that. That's just some language so that we can start this synthetic division and factoring thing. We're going to start here. Recall. If I gave you that and asked you to factor it, this is kind of a rhetorical question, could you factor it? Hopefully the answer is yes. You could do this, right? AC method maybe. Come up with two numbers. And then go through the whole process. And you would come up with x minus 4, x plus 1. Right? That's the way that you were taught to factor, or maybe you weren't taught that, but you were taught some way of factoring this. Agreed? Okay. We are going to use a brand new technique today to factor. And it's going to be using this thing called synthetic division. And for a lot of students, they've never seen it before. So I have to start and kind of act like you haven't. So here's the way synthetic division is going to work. Here's what I'd like for us to do. Keep this in mind, okay? Keep this problem in mind. What I'd like for you to do is I'd like for you to take that expression. I'd like for you to look at the numbers in front of each term, so the coefficients. Make sure it's in descending order. What are the numbers? Just the numbers by themselves. What are they? 1, -3, and -4, right? I want you to come over here and do this. This is like an upside down division box. And I want you to put those three numbers. 1, -3, and -4. Okay? I'm going to erase this factoring thing because I don't want to even look at that for now. Okay, you see what I did? Threw that in there? Now, somebody just pick a number. Just give me some random number. Don't make crazy number. Small number. 5. Okay. I want you to put a 5 out here. Okay? Now, follow the pattern of what I'm about to do. Everyone understand these three numbers came from that? Everyone understand that number came from the back of the room? Yes? Okay. Take this number out front here, 1, and drop it straight down. Now, take this number 5, multiply it times this 1, and put that answer underneath that 3, negative 3. So what's 5 times 1? 5, put it right here, underneath that negative 3. Still there? Okay, now add these down. What's negative 3 plus 5? 2, right? Repeat the process. 5 times 2 is 10. Bring that up here. Put 10 here. Everyone see that? Add down, and what do you get? 6. Okay, that last number you get, I want you to put it like in a little, most books just do it like that. I don't know why they don't make it just like a box, but just put it like in a little corner to itself. That number 6 is very special, all right? Come back over here now. I would like for, what number was picked at random? What number did? 5, right? I'd like you to plug 5 into this right here. Right here. Tell me what you get. You get 5 squared minus 3 times 5 minus 4, don't you? Just plugging 5 into that? And you get 6. 25 minus 15 minus 4, and that is 6. Do you think that that is a coincidence? Absolutely not. It is always going to be this part right here, which we call the remainder. We call this synthetic division. The remainder is always what you would have gotten had you plugged that number into this expression. You believe it or not? Yes. So what should happen if I plug 0 into that? What should I get if I plug 0 into that? Negative 4? Let's try it. Plug 0. I mean, we could tell, right? Just plug 0 in there and just kills this off and this off and get negative 4. Well, let's try it over here. 1 comes down, right? What's 0 times 1? 0, right? Add down, negative 3. 0 times negative 3. 0, add down, negative 4, right? That just gives us a little more confidence that it is working. Now, I'm not here to prove to you it'll always work. You just have to take it on faith that that's always going to work. Now, how is this going to help us factor? Because that's really what we're trying to do. Okay. When we broke this down earlier, we said that coming into this class, we all knew how to factor that, right? That we could all get it to that. Doesn't that mean that I can look at this and I can tell myself right here, what would happen if I plug 4 in? 4. What would happen if I plug 4 into this? What's 4 minus 4? 0, right? If I plug 4 in here, I should get 0. What other number should I plug in and get 0? What other number would make one of these 0? Negative 1. If I make that negative 1, that should be 0 also, right? So I'd like for you to come over here. I'd like for you to put a 4 in here, and let's see what would happen. We should get a 0 out here, right? So 4, okay, bring the 1 straight down. 4 times 1 is 4, put it here, add down, we get 1, and then 4 times 1 is 4, and then add down, and we get 0. Yay, so we're satisfied that that gives you the same thing, right? Any questions on what I've done? This has to be in descending order, correct, for this to work. Which you should always be able to do, put them in descending order. Okay, now watch this. Watch this. Let's act like I don't know this, all right? Let's act like I don't know that for a second. And that somebody gave me this and they asked me to factor it. So I wrote out the numbers like this, and I just, on a whim, I tried 4, right? and 4 gave me 0. The fact that that's 0 lets me know that if I plug 0 into this, right, I get 0. I mean, sorry, if I plug 4 in, yeah, I get 0. Yes? So would you agree with this? This piece of information right here tells me that x minus 4 must be a factor. That this thing must break down to have x minus 4 in it like this. Because if I let 4 go into it, it should make it 0. Y'all see that? Now watch this. Look at these two numbers right here. What I'd like to write right next to this is use these two numbers like coefficients. Like remember this was 1, the 1 was in front of x squared, right? This was in front of x and this was in front of by itself, just a number. I'd like for you to write that 1 in front of an x, and then this 1, so bring the power down, no more x's. And this is x plus 1, isn't it? Do you all see that this is x minus 4 times x plus 1 is what that factors to be? I have to do another one because this one was just too much information all at one time. I'm going to start a brand new one, and let's see if we can somehow use this division to factor something. Let's do this. 2x squared minus 5x plus 2. Okay, I'm going to try and factor this, all right? Hold on. Hold on, we may not be quite ready for this. No, hold on. Let's save that. We'll come back to it. This has fractions, and I'm not ready for that yet. How about this one? X squared minus 4. Does everyone recognize that? What is that? Difference of squares, right? So you could factor this, right? X plus 2 times x minus 2 is what that should be. Some of you on your test got that taken off because you got it to that, but you never broke that down. I think it was that the first problem in the factoring. I think you factor out a 5x first, and you would have been left with that. All right, so let's act like we don't know how to factor this. I'm going to draw upside down division box, and then I'm going to put the coefficients in here. What are the coefficients? 1 and negative 4. But that's not going to be right. Negative 4 goes there, yes. What? 0. 0 for what? You don't have an x, right? Look, it starts out as a 1x squared. There's my 1. How many x's do I have? So we have to come down in order. We don't have any x's, right? There's no x's up there. And then now you're negative 4. So what I'm trying to get you to see is that this is the same as 1x squared plus no x's plus a 4. When you put it in descending order, you have to account for any gaps in your variable with zeros. Now we kind of know a little bit about this, okay? We kind of already know that certain numbers are going to work, right? What number do we know would work? 2? So let's just see what would happen with 2. If I put 2 here, 1 comes down, 2 times 1 is 2, add down I get 2, 2 times 2 is 4, and if I add those together I get 0. So that tells me that the 2 works, right, because I get 0. But the big result of what I'm trying to get at for this last little part of today is not so much that we got the 0. That is important, but this right here and this right here tell us what that factors to be. What does the 2 tell me that I have here? Close? X minus 2. That's the tricky one because what you know is that when you plug in a positive 2, it gives you 0. That means you need an x minus 2 as a factor. Okay? So this factor will always have opposite of this number here. This will just be written exactly the way it appears. So what should this be? The 1 is actually going to be in front of a what? X. So I have 1x, can I just write x? And then this is a positive 2, so I put plus 2. You see that that's our difference of squares right there? Now, what did we have to know in order to make this happen, though? There's something here subtly that I'm kind of trying to overlook unintentionally. I had to know to come in with a 2, right? To make this work. Because if you just would have picked anything, it may not have worked. Like, what if I had picked 3? Would it have worked? I would have had 1, 3, 3, 9, and that's not 0, right? So that does not mean I can factor it out. Use this to factor. This has to be a 0 for that to happen. So how did I know to use 2? Later on, next class, I will give you a way of figuring out what this number needs to be. All right, but not today. We just need to continue to practice. So how about this one? For those of you who don't believe in the power of this method, let me do something real quick. Oh wait, I think I brought my calculator. Yeah, I did. Has anyone seen this method before for factoring? Yes? Good. Okay, check this problem out. X cubed plus 4x squared minus 11x minus 30. Now let's go through and if you're asked to factor this, okay, those are the instructions. Factor. What's the technique that we would use on this according to when we first started this class? What will we do? GCF? Do you have anything? Okay. I heard 4 terms, grouping, right? So if we try grouping here, we split this right here, don't we? We pull a GCF out of the first 2. What would our GCF be? X squared. We'd be left with x plus 4, right? Then over here, we need to have x plus 4 again, don't we? In order for this to work? Can you make that happen? Is it even possible to make this happen? Well, you have to be able to get x plus 4 here, right? That has to happen for grouping to work. But I need to turn that x into a negative 11x, so I have to have a negative 11 out here, don't I? That would give me the first term. But does that give me negative 30? No, it gives me negative 44. And it doesn't matter what you try, nothing is going to work. So grouping will fail. Does that mean it can't be factored? No. That just means your methods don't work. So there is a way to do this, it's just nothing that you've seen, which is why we're here. Okay? So let me show you how we can factor that using what I brought here today. I'm going to draw an upside down division box. I'm going to put what numbers in that box? 1, 4, negative 11, negative 30. Make sure that you account for that 1 out front. Make sure it was in descending order. We have that. And now what I'm going to have to do is I'm going to have to come up with a number out here, right? And I'm going to make, I need that number to work out so that when I do all this stuff, I get what here? 0. Now next class I'll tell you where the number comes from, all right? For now I'm just going to give it to you, all right? So let's do a 3. See if it works. You bring 1 straight down. 3 times 1 is 3. We put it here. We add down, we get 7. You multiply 3 times 7, you get 21. You add down, you get 10. You multiply 3 times 10, you get 30. That's a remainder of 0. And we are happy campers, aren't we? No, I mean, just act like we're happy, okay? It worked, we got 0. What does that tell me? What do these numbers tell me? What does that number tell me? This is where we really have to get our head around this. What does this tell us? We have a factor of what? X minus 3. Now, last time we did this, we only had 2 numbers, right? Now we have 3. If we have 3, then what we have left here is not x and a number, it's now x squared and then an x term and then a number. So we're going to have 3 terms here, which means this, what's left here is going to be quadratic instead of just linear. So the 1 goes in front of x squared, then the 7 goes in front of x, and then this goes to 10. Another way to think of it, other teachers talk about it a different way. They always say that this first number, the power on that x, will always be 1 less than what you started with. So if you started with cubed, this first one would be squared. In the previous problems we did, we started with squared, so the first one we had was to the first power. Either way, I mean, you can look at it however you need to look at it. 3 terms means quadratic to me. 2 terms means linear. What would 4 of these mean? That we would have an x cubed, and then an x squared, and then an x, and then a number, which we will have. Okay, we're headed there. But so now what? What we're saying is that that is the same as this. If you don't believe it, multiply it out, expand this, and you will get that. But I'm trying to factor it down, so I need to try and tear that down further. So how can I tear that down further? What about this, right here? That's quadratic, right? You could factor that using AC method. But why do that? Why don't we just do synthetic division again? Right? Why not? I mean, it works. Why not just use it again? Unless you can do that mentally. If you can just look at that and do it, then you're done. So let's act like we can. So here's where I am. I'm going to start this over. I'm going to do my synthetic again. What are the numbers I'm putting in now? 1, 7, 10. Now, again, I'm hiding from you what numbers to use, right? I'm not telling you right now. But the next one that'll work would be -2. So let's work this out. 1, -2 comes down, -2, add down, you get 5. -2 and 5 gives you -10, add down, you get 0. What does that tell you? This is an x plus 2, and then these 2 numbers, x plus 5. And that part right there, x plus 2 times x plus 5, is actually these 3 together, right? These 3 come from those 2. So we still have that one out there, don't we? So this up here, okay, this right here, factors is equal to the x minus 3 we had out front, then the x plus 2, then the x plus 5. If you were to multiply all those out, you would get that. Pardon me? Okay, this is like the 1 here is like the 1, and then the 5 here is the 5. Because there were 2 of them. The thing is, the powers keep coming down, and the last one has to be a number. So you can say number, and then the power comes up, and that's x. Is that okay to say it that way? You okay?
So there's 3 numbers to start from x squared.
That's right. 3 numbers it would start at x squared. 2 numbers starts at x. You won't ever have 1 number. So. Okay, so I mean, this is really like a new way of factoring, isn't it? The key, though, is still how am I coming up with those numbers? That's still kind of the hidden secret. One more. This one that we did on your test, that everyone, practically everyone missed that one. It's a difference of cubes. So there's a formula for this, but I forgot the formula. So I'm going to try something. What are the numbers that go in here? Be careful. 1, 0, 0 again, negative 27 now. So we have a 1 in front of the x cubed. We don't have an x squared, so a 0. We don't have an x, so a 0. And then we have negative 27. So that's our synthetic division box. And now we come up with the number, right? So let's go with 3. Bring this down, we have 1. 3 times 1 is 3. Add down, we get 3. 3 times 3 is 9. Add down again, we get 9. 3 times 9 is 27. And then you get 0. Which is what we need for this to work. So what does this give us? A factor of x minus 3, right? And then we have 3 numbers, so we know it's going to start with squared. 1x squared plus 3x plus 9. Now going back to the problem that I gave you on the test, you were supposed to see that this was the same as x cubed minus 3 cubed, and then you were supposed to use that formula x minus a. I think that was the formula that we used, x plus, oh no, it was, I used a and b, didn't I? The formula we had was a cubed minus b cubed was equal to a minus b times a squared plus ab plus b squared, right? That's what I gave you in class. So you're supposed to realize that your x is your a and your 3 is your b. So this should have been x minus 3, then whatever a is, so that's x squared, then a times b, which would have been 3 times x, and then plus b squared, which would have been 3 squared, which would have been 9. So same thing, no formula necessary. Now the question is, though, does this break down further? It turns out it does not, only because it is difference of cubes. If this formula, if this quadratic could go down further, then they wouldn't use this formula. They would actually have broken it down for you in the formula. So we will not be able to break that down any further, but let's not get into that right now. I just wanted to show you that I get the same result that you get using that formula doing synthetic division. Is it okay?
How do you know you can't break down that if you find out later
Well, no, I mean, you mean, how can I tell by,
that we could
Like,
use?
how can I work? 2 ways. If you have a difference of cubes, okay, you would have to recognize that. Difference of cubes, whenever you write this formula, that will never break down further. Never, ever. Okay?
If you have difference.
If it's a difference of cubes. Now, if you were over here and you didn't realize you had difference of cubes, and someone gave you that problem, the way that you could figure out that that does not break down, there's a couple of different things we could do. But again, we're not really there. What you could do is, remember the quadratic formula we had? Negative b plus or minus square root b squared minus 4ac all over 2a. Remember all that? Yes? This piece right here has a name to it. It's called the discriminant. This piece underneath the root is called the discriminant. If you just look at the discriminant, so that would be b squared, 3 is b, right? Square it, you get 9. Minus 4 times a, for us, a is 1, times c for us is 9. Then you get 9 minus 36, don't you? Okay, 9 minus 36. That's a negative number, isn't it? You cannot take the square root of a negative number. So if the discriminant is negative, that doesn't factor. But I'm not going to make you, but you asked a good question, like how would you know that doesn't work? Well, because you could check, you could do a discriminant check to show it doesn't factor. All right. So what are we looking forward to next class? Finding out how we know that number, right? Now this is extremely powerful because if we can actually do this, there is really no limit to the degree of polynomial we can actually solve. I mean, we can go as high as you want in factor and just keep on applying this over and over and over and over. All right? So homework out of here. I don't think we're ready for homework out of here. Maybe. Let's see. I can give you something out of 3.2 just to. How about this? On page 312, look at numbers 51 through 54. I'll just give you those problems, all right? That's not a whole lot, but all they're asking in these problems is something like this. Because I didn't do this on the board, I want you to see what they're asking. They give you a function like this. Okay? And then they say x equals 3. And they say use the factor theorem to show that the given value is a 0 of this function. So what would happen if we plug 3 into this? We plug x equals 3 in here, we get 9, take away 6, take away 3, right? That's 0. That's not what they're asking for. What they're asking for is this. Do synthetic division and put 3 out here and show that when you do this, you get a remainder of 0. It's just practicing doing this. That's all it is. All right? Just a couple problems like that. You good? Don't forget to also do that homework. Have a good rest of your day. See you Thursday. Yeah, that one, just you do this problem and then do these. These are out of the book, and then that one just graph that. Yes, the 7 steps for that. Sir.
Are you done? I was here.
First day?
Yeah,
Or
the
second?
second day. That's the day I went in.